welcome to my talk. Today I will give a talk about online matching, but fractional version, and we improve the lower bound of the competitive ratio. It's a joint work with Zhihao Tang again, and he is here. I do not put photos on it because I'm here and he's here. Okay. To begin with, I start with the classical online bipartite matching model proposed by Kapasrani and Masrani in 1990. It's similar than the resource allocation in the last talk. We have an underlying bipartite graph, but only one side vertices is given up front. It's called offline vertices. And another side is online vertices. They will arrive one by one. Only at the arrival time of a new vertex, I will know which offline vertex is connected to him and which one is not. And the important thing is we need to do matching decisions immediately after an online vertex arrives. And we can decide to match it to one offline vertex or just keep it unmatched. And the important thing is the matching decision is irrevocable. We cannot change it in later time. And I will go to maximize cardinality, and we will analyze the algorithm by compatibility ratio. You have already know it in last talks. Okay, and the good thing is the online bipattern matching is really well installed with respect to the compatibility ratio. Like if we consider deterministic algorithm, we know greedy is the best choice. Greedy just means when online vertex come, I will arbitrarily choose a matched neighbor. Do it again and again. It is a deterministic algorithm, and it is 0.5 competitive, and the competitive ratio is optimal among all deterministic algorithms. And if we allow randomness, we can do better. There's an algorithm called ranking can achieve 1 minus 1 over E competitive in expectation. And it is also optimal among all randomized algorithms. And furthermore, if we further to allow fractional matching, it means we can do matching fractionally. And online vertex come, I can match half of it to the first vertex, half of it to the second vertex. It is allowed. We only need to promise the total match quotient 1. If it is allowed, we can use another algorithm called water filling to also achieve 1 minus 1 over E compatibility. And it is also optimal among all fractional algorithms. It is really well stored model. And this model has many applications like online advertising or other things. In that setting, the offline vertex may represent the advertisement in the system. We need to present them to some users, and the users is the online vertices. Right, it is very natural. But the question is, in some other applications, offline vertex is not acceptable. Like, for example, the Uber scenario, we have two kinds of vertices. It's also a bipartite graph, passengers and drivers, but both of them will arrive on. In some time, a passenger release a request, I need a car, and sometimes a driver give a request, I need a passenger. These things are all online. And one other different thing is we actually do not need to make matching decisions immediately after when the users or passengers arrive. We can wait some time. They will wait some time in my system. I can match them anytime they stay in the system. Okay, so there's some difference. So how to formalize it? There's another model, fortunately, called fully online matching. There's also an underlying graph, but now no offline side. Everyone is online. And we have two critical time now, not only the arrival time, and vertex have an arriving time and a deadline. The arriving time means the time he get into the system. And at this time, we will know the connection information between it and all already arrived vertices. I remark here that we cannot have an edge between arrival vertex and the left vertex. It is not reasonable. And And there's another time called deadline. It is the last time the vertex stay in the system, and it is the last chance we can match it. Oh, okay. Deadline. And I further remark that after it leaves, we will never have a further connection for future vertices. Okay, that is the model. Is the model clear?
Is the deadline any different than the last time that neighbor arrived?
Yeah. We will not have few further neighbors. So,
Question. Do you get to see the deadline of a node when it arrives or only when it leaves?
yeah, we do not need to know, but he need to tell me when the deadline arrives. Yeah. He cannot just leave and don't tell me. It is really hard. Okay. There's also several works for this model, but not so well understood. Some of them do not have height ratios. Deterministic is also easy. Greedy is not optimal. It is because of the same reason. For randomized algorithm, first people try ranking the optimal algorithm in the one-sided version. And finally, they find the compatibility ratio of ranking in this model is 0.567, but not optimal because we have another algorithm called balanced ranking. It means the rankings compatibility ratio to only a little, 0.569. And I believe it is not optimal. And there's a little remark. The balanced ranking algorithm is actually ranking based, but it gets some suggestions from the optimal fractional algorithm. Water feeding. Oh, the water feeding algorithm is not optimal in this setting too, but it is better than the ranking algorithm, so we can get some suggestions from the fractional algorithm. It somehow shows the importance to study fractional. Okay, for the fractional version, water feeding, the optimal algorithm in one-sided version, only 0.585. I can remark that 1 minus over e is about 0.632. Okay. And later, the ratio has been improved by another algorithm called eager water feeding. It is water feeding based, but do some improvement. And for the hardness side, the upper bound, the previous best result is 0.629. It is strictly smaller than 1 minus over e, so the model is strictly harder than the one-sided version. Okay, so move to our results. It's very easy to say we just improved the lower bound, upper bound. For fractional version, we improved the lower bound, the compatibility ratio. We designed new algorithm to which have a compatibility ratio 0.6. And for the upper bound for the hardest, we also improved something. We improved the ratio from 0.629 to 0.613. We also have some improvement for another model called general vertex arrival. I do not include the introduction of this result in this talk, but I can tell you the general vertex arrival is also a model that allows every vertex arrive online. But difference is, roughly speaking, it's only allowed to make matching decision at arrival, but not deadlines. There's no deadline in the model. Okay. We improved the upper bound hardness of that model to 0.584. And another interesting point is we also designed another algorithm in general arrival, but surprisingly, it achieved really the same ratio as 0.526 as the previous algorithm. They are different algorithms, but achieve the same ratio. Okay. Different analysis. Okay. And the main take-home technical information I want to share is we found out it's really important to use something called historical information in the fully online setting. So what is that? Maybe I just start with the fractional algorithm water feeding. Okay, I forgot I get that page to show why we need to study fractional algorithms. Yeah, 2 reasons. One reason is fractional algorithm usually can lead to a good randomized algorithm. Maybe by rounding, maybe just give some suggestions. And another thing is fractional algorithm may itself well motivated. Let's think if a vertex do not just denote one user in the real world, it denotes as group of users. They come together, share similar they're really similar, have equally connection between offline vertices, then we can match them together, right? Match some fraction means match some of them. It is itself well motivated in some cases. And let me introduce the fractional algorithm water filling. It is optimal in one-sided version and also achieve a good compare ratio in three-sided version. The key idea is we will do fractional matching, but every time we will try to match a vertex with smallest matched portion. I use water level to denote the already matched portion of our vertex. We will always match the vertex with lowest water level. It is really like water filling, so it's called water filling. The real procedure is when the online vertex come, we will continuously match small portion of that online vertex. And every time I let the small portion goes to the lowest water level. It is the algorithm. Let's see a very simple example. This is the arriving vertex, and the two offline vertex already have 0.5 matched portion. So because you have two neighbors, one with match portion 0, one with match portion 0.5, the first half portion of U will go to the 0 vertex, right? And then the two vertices will grow the match portion simultaneously, and they will become 3/4. That is the water filling algorithm. Okay. And so what is historical information? Historical information is something help us making matching decisions. When an online vertex come, I need to choose A or choose B, choose a neighbor, or fractionally choose a neighbor. But why? It must because of some reason, right? The reason is the historical information. Like the water level is somehow a historical information, the already matched portion. In the online by pattern matching model, the one-sided model, actually, why water filling algorithm is optimal? It is because in the worst case, no other information can be used. So it's become optimal. But in the fully online matching model, we find that in the tight case of water filling, there's actually some other historical information can be used. We have already observed some special graph property, graph structure, and we can use them. Let's see why. It is the hard instance of water filling in the one-sided version, the well-known upper triangle. The left-hand side is offline vertices, the right-hand side is online vertices. The online vertices arrives from top to down. And when the first online vertex will connect to all offline vertices, the second online vertex will connect to offline vertex from 2 to n, the third one 3 to n. And you can check if we run water filling on it, the first online vertex will give every offline vertex 1 over n. The second one will give 1 over n minus 1, and so on and so forth. Okay. And after various straightforward calculation, we will find that the water filling algorithm will match 1 minus 1 over e. But the optimal algorithm can match everyone. It is because we do not know which one is the perfect one, but the offline algorithm know. And it's also easy to observe this hard instance is really history-free. Because you can check, every online vertex have many neighbors. These neighbors seems exactly the same as others. We do not know why we should select one match more portion to someone specific, because it looks exactly the same. The only historical information we can use is the water level. There's no other graph structures. But let's see the hard instance for fully online matching. I remark here that the fully online matching, the water filling algorithm means we will do water filling at deadline, okay? And in that case, we have multiple copies of the upper triangle. Like that, we have around three copies of upper triangles. And in this case, I will call the online side because it is actually fully online. Everyone is online, but I can simulate online side and offline side by different deadline order. For example, I let C3 vertices deadline earlier than C3, and the left-hand side becomes the decision side. These are the people who make matching decisions. So I call them decision vertices. And each copy have different decision vertices. Sometimes on the left, sometimes on the right. And the key point to make water filling perform worse than the one-sided version is that we have some edges between the decision vertices. You can see the result. What happens if we have these edges? When the decision vertex make matching decisions, he already has some water level, right? It is different than before. Previously, we make matching decisions at arrival, and the water level is promised to be 0, but now it's not. I do not show how to calculate it, but I can tell you it makes the ratio worse. So, and the ratio is just 0.585, the same as the combined ratio of water filling in the fully online model. So the problem is, can we make it problem hardness? What is time?
Yeah.
Okay. Can we make it a problem hardness? If it is also history free, we can make it. Let's check. We just check this an arbitrary online vertex, an arbitrary decision vertex U, to see whether we can find some historical information. If we want it to be historical free, directed idea, naive idea is we can let these vertices arrive later, and then the same as the upper triangle, all use neighbors looks exactly the same. If we can do it, it is history free, it is a problem harness. But we cannot do it. Let's check U1 and U2. It have some connection between the last round, right? Because they have some connection between the last round, when last round's decision vertex make matching decisions, we should know them, right? We should know U1 and U2 in the system. So U1 and U2 must arrive earlier than the deadline of U. So what happens? Then when you make matching decisions, his neighbors does not look the same. Say we have some historical information. One rough way to use it is that by this historical information, I can observe which vertex is in this round, which vertex is in the next round. Then we can totally omit the next round vertices. We just make matching decisions in the same round, and it can at least get 1 minus over E. Not so bad. So that is why historical information becomes really important in the fully online matching model. So how to use it in someone already know naive way, a very interesting way to use it. It is called eager matching. And if we use eager matching in water filling, then it becomes algorithm eager water filling. What is eager matching? We will do some matching decision at arrival, but do not make every matching decisions postponed to the deadline. It may be tricky to you because it is easy to prove making matching decision at the deadline is really better. But why we need to do some matching decision at the arrival time is somehow we just want to use some historical graph information. It's hard to explain, but I can explain a little bit why eager matching can beat the hard instance in the previous page. Because in the previous page, the ratio become really bad because we need a really bad deadline order. But if decision order, really bad decision order. But if we do something at arrival time, I somehow perturb the decision order. Perturb the decision order, so it will not be so bad. And for analysis, to prove the eager water filling can really beat water filling, we need an economic view of the algorithm and need some parameter analysis. We can view that each vertex have a price P based on water level. And we use a function f to set the price. And whenever we match an edge for delta portion, I will let V get PV times delta money and let U get 1 minus PV delta money, the remaining part. So by this economic view, and very natural thing is when you choose partner, when you choose how to match, he will choose the cheapest one. And if fx is a non-decreasing function, it is same as water filling. And there is also something to discuss. When should we stop eager matching? It also depends on price. And finally, how to prove the compounding ratio? By using a prime framework, if we can prove for every edge, the money of U plus the money of V is at least gamma, and we can prove gamma competitive. It's because of prime property. It is the previous approach. Finally, we move to our approach. Is there's a little time, I just make it very roughly. Okay. The key things, only one word. We find out that the eager matching can capture some historical information, but the price function does not. So we design a historical based price function embedded with the eager matching, then we achieve a better configuration. That's the idea. So it's all. And finally, I really want to push the bound to be tight. So I think a little bit more. One thing I want to say is to achieve tight bound, we really need a very super historical pricing function. Not quite simple. And if you are interested, we may discuss later. Thank you.